I'm Vinay Kumar, and I'll be presenting Relaxed Local Correctability from Local Testing. This is joint work with Jeffrey Mott. Let me first briefly define what an error correcting code is. A code is a subset of bit strings, and we say it has distance delta if for every pair of bit strings in the code, its Hamming distance is at least delta. The rate of C measures the redundancy of the code, and it's defined to be the log of the size of C divided by n. You can sort of think of it as how dense C is. So we call a code to be locally correctable if they have a corrector algorithm. And what is this corrector algorithm? So let's say we're given a word W, and we know that it's delta close to the code. This delta will be called the correcting radius. So a corrector on index I will query only a few bits of W. It will only look at Q positions of W. And from that, it'll be able to output the ith bit of the closest code word with high probability. So this is called local because I'm only looking at a small number of places in W. So this is very useful as an object in TCS. However, constructing optimal LCCs has proven to be a really big challenge. So, for example, let's say we constrain our code to have at least constant rate and at least constant correcting radius. So this is called asymptotically good. The question is, what's the minimum query complexity that you need for the corrector? So seminal work of Kotz and Trevisan showed that you do need log-n queries. In particular, you cannot hope to get a constant query complexity as well. Well, what's the best upper bound that we know? So construction of Koparty-Mer, Ranzawi, and Saraf gives a 2 to the square root log n upper bound. But as far as log n and 2 to the root log n, we have no idea what the true optimal query complexity should be. So there's a big C between the lower bound and upper bound. To further drive this point, trying to construct better LCC is a problem that's been attacked for a long time, since the 1990s. For a while, the state of the art remained at a small polynomial factor, which was first done in the early 1990s, and then high rate versions of the code, along with alternate constructions, were done recently in the 2010s. And then the breakthrough work of Koparty-Mer, Ranzawi, and Saraf finally broke the polynomial barrier. However, this is our current state of affairs, and despite many years of working on this, there's still a big gap between the lower and upper bound. With this in mind, we might hope to perhaps relax the definition and then see if we can construct optimal codes in this relaxed sense. But of course, we need to make sure we don't relax it too much so that the code becomes useless. So one way we can relax the definition is to allow the corrector to give up if it detects errors. So the definition we had says that even if a word is not a code word, it better output. And even if the ith bit is corrupted, it better output the correct ith bit of the closest code word with good probability. So this is definitely a relaxation, right? If we can just simply output an error message instead of working hard to find the true correct ith bit of the code word. And so the question now is this relaxation sensible, or does it destroy everything we wanted in an LCC? And we have reason to believe that it indeed is still useful. A main application of LDCs is for constructing PCPs. And in that context, we usually have some instance X that we want to show is in a language, and then a purported proof that X is in the language. And we want to be able to only look at small number of bits in the proof to verify. And usually what it's done is that our proof is encoded in some code so that we can then spot check the proof to read it. There's usually two phases. So in the beginning, you locally test pi to make sure that it follows the right template of the proof so that it is actually a code word. And then we reject otherwise. And then once we're confident that it is a code word, we now use local correctability. We now actually extract information from the proof, and then we check that indeed corroborates X. So from this flowchart, you can see that actually in the second phase, if the second phase detects errors, we can reject it, right? Because uh, the first phase literally rejects the proof if it does detect errors. And so if in the second phase we happen to detect errors, we'd want to reject it anyway, right? Because that means this proof is not of a valid form. And of course, we can reject it. Therefore, local correctability can be replaced with relaxed local correctability for PCPs. So let me formally define what an RLCC is. It's similar to an LCC, right? It's a code, and we say it's an RLCC with Q queries, correcting rate is delta. If there's a corrector that makes Q queries, so that for all W that's delta close to our code, then for all indices I, our corrector on input I will query Q bits of W and will be able to output the ith bit of the closest code word or an error message or an error symbol with probably at least 2/3. So this error message is the relaxation. However, as said, this is a very trivial definition because our corrector can just always output bot and it'll always have this desired behavior. And so in order for it to actually give information, we will stipulate that if W is indeed a code word, it needs to output the ith bit. So it'll never reject when W is in the code. So in the same paper that defined these, they also constructed RLCCs that are much better than known LDC constructions. So this really showed that this relaxation gives you savings. And furthermore, this relaxation does not eliminate this relaxation does not make such a code useless. In fact, there's been many applications of RLCCs beyond PCPs even, proofs of proximity, property testing, as well as data structure. So what is the state of the art for RLCCs? So our lower bound is about the same as LCCs. It's a square root log n. But now, how good is our upper bound? How close to square root log n is it? So of course, existing LCCs are LCCs, and they'll have query complexity, right, 2 to the square root log n, as we said. And then following that work, there were actually better RLCCs constructed. In fact, in 2020, there was RLCCs with query complexity log n to the order log n, and follow-up work that gets query complexity log n to the log n. So this is works of Gur, Ryan, and Rothblum, and Cohn and Yankovitz, respectively. And so already this is like an extremely better picture, right? Because now we're almost polynomially close to the query complexity lower bound. It's a constant, it's between a log n factor and dx. And so this begs the question, can we match the lower bound up to a polynomial factor? And our work is the first to do this. We create RLCCs with log n to the 69 query complexity. And we wish to also point out that follow-up work of Cohn and Yankovitz construct codes with query complexity log n squared. And so thus, the gap between the lower and upper bound is extremely close. It's either square root log n, it's between square root log n and log n squared. Great. So what is the approach that we use? It's actually quite similar to the approach of previous work, So we want to construct a relaxed locally correctable code with arbitrarily large block length n, right? And to do that, we're going to start with a really small code, right? We're going to start with a code of block length so tiny that it's trivially local, right? Because if I have a code of block length log n, of course, it's going to be local because if I query every single bit, that's only log n queries. So I'm going to start with a tiny block length, and then I'm going to gradually boost the block length iterative by applying some operation. So I'm going to use a smaller RLCC to make a bigger one, and then a bigger one, and a bigger one until I reach block length n. So both previous works followed this approach, and we will too, although with a different twist. So let's kind of briefly go over the previous approach and why it wasn't able to get polylog query complexity. So Guron, Ryan, and Rothblum used tensoring to boost block length. So what is the tensoring of codes? If C is a linear code, then C cross C is the code where you have an n by n square, and you stipulate that every row is in C, and also every column is in C. Guron, Ryan, and Rothblum show that if C is an RLCC, then C tensor C is also an RLCC, and the block length squares. So why is the tensor product an RLCC? Well, the idea is that, okay, if I want to correct an index I, I'm first going to run the C corrector on the row containing the index that we need. What this will do is it'll check that the index I fits well among the row that it's in. However, this row might not fit in with the rest of the square, and so we need to cross-check the columns as well, right? So for polylog n different indices in the row, we want to check that they fit in well with the columns they're in. And so what happens is we're now running the corrector on the smaller RLCC, polylog n many times. So thus, whenever we iterate, whenever we tensor, the query complexity multiplies by polylog n. And how many times do we iterate? Well, we'll iterate log n many times because if you start with the small, if you want to reach block length n, you need to square log n many times. And this gets log into the log n query complexity. Follow-up work by Cohen and Yankovitz improved the query factor per step to polylog n rather than log n. And thus, they get a log n to the log n query complexity, which is equal to log n to the log n. So as you can see, the reason why we can't get polylog n query complexity with this approach is because we multiply, the query complexity multiplies at each step. At each step, we're multiplying by some polylog n factor. And then this adds up, and then this like builds up. And then since there's a super constant amount of recursive layers, we end up being super polylog. So the question is, what if we could have an additive query cost, right? Because if we had an additive query cost, we're okay with a polylog n cost per recursion. And then we're even okay if there's up to a polylog n amount of recursive layers we have to do, because then overall we'll have polylog n query complexity. So in order to help us get an additive query complexity cost, we can't recurse many times per iterations. And so what we're going to do is we're going to use some outside help so that we can reduce the amount of times we recurse to just one. And what are we going to use? Well, we're going to use a huge hammer, locally testable codes. So briefly, a locally testable code can detect corruption locally. Okay, so in particular, it only has to make Q queries, and it'll be able to reject the code word with probability proportional to the distance of the code. In other words, the farther away the word is from the code, the more likely my tester will reject the code. And then the proportion, the factor of rejection is called the testability factor, and it's this kappa. We also stipulate that if it is a code word, if W is a code word, T cannot reject. T should never reject. So recent breakthrough work of Dinur, Evra, Livne, Lubotsky, and Moses give extremely good high rate LTCs with very good parameters. And what we're going to do is we're going to use these high rate LTCs to iteratively construct bigger RLCCs. How are we going to do this? Well, instead of tensoring, we're going to define a new operation that we call nesting. Okay, so what is nesting? Let C1 be a small code of block length little n, C2 be a code of block length big N, and for simplicity, let's say n evenly divides big N. And what we're going to do is we're going to define C2 nest C1 to be the code C2 intersected with big N over little n copies of C1. Okay, right? So C2 has block length big N. C1 repeated big N over little n times is also a block length big N code, and we're going to take the intersection of this. And note this is the direct product. So it's like C1 to the big N over little n is just big N over little n independent copies of C1. So pictorially, let's say we have small code C1, and then we have a big code C2 that's twice as large as C1. Then a code word that's in C2 nest C1, what will that look like? Well, if you look at the whole code word, that'll be inside C2, the big code. And then if you look at all the smaller blocks, they will be in C1. So if you look at the first half, it'll be in C1. If I look at the second half, it'll also be in C1. And so in general, right, if C2 was 5 times as big, then if you split it into fifths, each fifth will be the smaller code. And that's exactly what nesting is. We note that n need not divide n. It's just a technical, some small technical thing you have to do to bypass this. And what we show is that an LTC, if you nest a smaller RLCC inside a bigger LTC, you get a bigger RLCC. In particular, you get a bigger RLCC whose correcting radius does not decay. So again, this is the image. We have a big LTC, and then we have smaller RLCCs nested in it. Why is this the case? Well, what we're going to do is say we want to correct index I. If the number of corrupted bits is really small, the idea is that we can then look at the RLCC, the smaller RLCC that contains index I, and recurse on that. And then if the number of corrupted bits is above this threshold, then we have a lower bound on distance, and so our local tester can detect errors. So let's do the near case first. Let's say we have some code word W that's within the correcting radius of our RLCC. And let C be the code word closest to W. If the number of corrupted bits is really small, in particular it's less than delta times little n, let's look at the block, the RLCC block that contains bit I. Notice that even if all delta n corruptions were inside this block, this will contribute relative distance at most delta, right? Because the block length is n, and so that means the distance from W to the closest code word when restricted to this block is still at most delta. We also know the closest code word restricted to this block is inside our RLCC by construction. That means our word restricted to this block is within the correcting radius of our RLCC. Therefore, we can just call the corrector on the smaller RLCC, and we'll be able to relax correct the ith bit. Perfect. So now what if we're in the far case? What if the number of corrupted bits is greater than delta n? Well, that means we have a lower bound on the distance, and we can call the local tester on the whole block, on the whole word. So in particular, right, our distance is now lower bounded by this. And therefore, a tester will reject with probability kappa times that quantity. And then therefore, if we repeat the tester independently, a reciprocal of that probability number of times, we'll be able to find corruption with high probability. Great. So in both cases, we win, right? In the close case, we recurse on the smaller RLCC containing the bit, and in the far case, we'll find corruption by using the local tester. And so that's exactly how we construct a local corrector. We first run the LTC many times, and if any detect error, we output bot. Otherwise, we recurse on the interval containing up. Notice that we only recurse once. Therefore, nesting only adds some factor times QLTC more queries. So this is an additive increase, right? So what nesting did is it boosted the block length, it preserved the correcting radius, and it only added a small query complexity cost. Great. So one thing is whether nesting destroyed the rate of the code, right? Because we did a lot of intersections. So what if nesting destroyed the rate? So here's where we use the linearity of our codes. So if these codes are all linear, you can show by constraint counting that if LTC has rate 1 minus epsilon LTC, RLCC has rate 1 minus epsilon, then the nesting LTC nest RLCC will have rate 1 minus epsilon LTC. So it's just an additive loss in rate as well. Great. So how are we going to construct our final RLCC? Well, we'll iteratively nest with the larger and larger family of LTCs. Okay? So what we do is we're going to take increasing family of LTCs and nest them with each other. So in particular, we're going to have LTC1, LTC2 of increasing block length. They're going to have the same distance to delta. They're going to have query complexity Q and rate 1 minus epsilon. And so what's going to happen is the final code word, if I nest LTC1 with LTC2 and then LTC3 and then all the way into LTCM, it's going to inherit the final block length of n sub m. The correcting radius is preserved. And then the query complexity has this additive factor, as we stated. And then the rate decays additively as well, right? And since there's m many LTCs that we use, the rate will be 1 minus m times epsilon. Great. So now let's do some simplification assumptions. Let's say there's a fixed ratio between consecutive block lengths of our LTCs. This will give some nice simplifications in our query complexity and rate. Great. So visually, how does this look, right? We have this syntactically. Visually, we're going to have our big LTC M, and then we're going to nest smaller LTCs into this big LTC. And then we're going to nest even smaller LTCs into those smaller LTCs, and so on and so forth, creating this tree structure. So notice that M, right, the depth of this recursion is simply log base R of n, where, if you recall, R is the ratio of consecutive block lengths. So we now know that C is an RLCC with the following parameters. And so now let's instantiate them with the del M codes. So what they showed is the following. For any small epsilon, you'll get an infinite family of LTCs with the following parameters. And so one thing to note is that we want our rate to be constant, right? So that means our epsilon needs to be at most 1 over log n. And so let's plug that into our LTC construction, and we get the following. So now let's plug these LTC parameters back into the left and see what we get. And if you do the math, you'll get the following parameters. We'll have really high rate. We'll have log into the 69 query complexity. But unfortunately, we're going to have subconstant correcting radius. However, this is an easy fix. Why? We just need to nest one more time with an LTC with constant radius and constant rate. So the radius will then inherit this large LTC distance, and then the rate will deteriorate down to a constant, but that's fine. Therefore, all in all, we will get asymptotically good RLCCs with query complexity log n to the 69. So we do have some open questions left, right? So Kohn and Yankovitz improved the queries to log squared n, but it's now open what the true optimal parameter is. Is it log n? Is it squared log n? This is a very interesting open question. It is also of interest to the PCP community to construct an RLCC, which is also an LTC. Because if you recall earlier, we said that a PCP needs local testability and relaxed local correctability. On this end, the best known construction is log n to the log n. Thank you.